Many electronic circuits are named for the function they perform. The voltage doubler is such a circuit. It develops a voltage equal for all practical purposes to twice the peak voltage of the input. The Air Force uses several types of voltage doubler circuits. Each one is designed for a particular circuit application. One such application of the voltage doubler is in the high voltage section of this oscilloscope. The rectifying action of the voltage doubler is similar to that of other types of rectifier circuits in that it converts an AC voltage into a DC voltage. And it can operate as a full-wave rectifying device whereby it doubles the input to output frequency. Since the voltage doubler is similar to other rectifiers, we'll use this bridge rectifier circuit to demonstrate the principles of voltage doubler operation. It consists of a transformer, 4 diodes, and the load in the circuit is represented by a variable resistor which we've labeled RL. The circuit is made operative by turning S1 on, which applies power to the transformer primary. The rectifier circuit consists of diodes CR1, CR2, CR3, CR4, and as previously mentioned, RL, a variable resistor. The circuit develops an output peak voltage as seen on this oscilloscope, which we've connected across the output. Now the lower trace represents the input AC signal, and the upper trace represents the output DC voltage. Okay, now let's change this circuit slightly. We've removed CR3 and CR4 from the bridge circuit and substituted 2 capacitors. Notice that the peak output voltage of the circuit has increased to nearly twice that of the bridge. So what we've accomplished by placing these 2 capacitors in series, that C1 and C2, is change the operation of the circuit from a bridge rectifier to a voltage doubler. A more common way of drawing the voltage doubler circuit is shown here. Now, this arrangement shows that the voltages of C1 and C2 will add since they're placed in series with each other. Now, this means that the output then equals the sum total of the voltages developed by both capacitors. This voltage doubler circuit, operating as a full-wave rectifying device, develops an output pulse between here and ground on both the negative and positive alternations of the input signal. If we begin circuit operation when the input signal is negative to positive across the transformer secondary, then the anode of CR1 is positive, and likewise the cathode of CR2 is also positive. Now, in order for a diode to conduct, we know that the diode must be forward biased, or its anode must be positive with respect to its cathode. CR1 meets this requirement, so it conducts. Its conduction path is from the negative side of the transformer secondary across, up through C1, charging C1 negative to positive. Now, through the conducting diode, CR1, back to the positive side of the transformer secondary. During conduction time, CR1 is effectively a short. Therefore, C1 charges to the peak voltage of the transformer secondary. If the peak of the secondary equaled 200 volts, C1 at this time would be charged to this value. Now, for the sake of explanation, let's leave C1 charged and consider the negative alternation of the input signal. Reversing the polarity on the transformer secondary means that the anode of CR1 is now negative, and the cathode of CR2 is also negative. Therefore, CR2 is forward biased, and it will conduct. Its conduction path is from the negative point in the transformer secondary, down through the diode CR2, up through C2, charging C2 negative to positive, then returning to the positive transformer secondary. C2 is now charged to 200 volts, or the same value that C1 was charged to on the positive alternation. Now this means that during one cycle of the input signal, we develop in the output the total of C1 and C2, or 400 volts. This voltage value equals nearly twice the peak voltage of the transformer secondary. Therefore, we get the name voltage doubler. Now, let's determine the effects that the load has on the voltage doubler. Now, the effect of a load change on the output voltage can be demonstrated quite effectively using this circuit. The load resistance, represented by the variable resistor, is now at maximum resistance. Therefore, output voltage is maximum for this resistance, and output current would be minimum. Now, decreasing the value of resistance or increasing the load increases the current drain, and the average output voltage decreases. Notice also that the ripple amplitude has increased. Now, these effects on a load change occur because the load change changes the discharge time of the capacitors. If we isolate C1, C2, and RL from the diodes, the discharge path for C1 and C2 is through each other and the load. Now, since it takes time to discharge the capacitors, and since the time constant equals resistance times capacitance, or R times C, the higher the value of resistance and capacitance, the longer the time for one time constant. With a long time constant, where the resistance is high, average output voltage is high. If the load on the circuit increases, resistance decreases, and this decrease in resistance shortens the time for one time constant. This then allows the capacitors, that's C1 and C2 in this circuit, to discharge a greater amount between cycles of the input. So, average output voltage decreases. By isolating a portion of the circuit, namely C1, C2, and the load, we've been able to analyze several important facts pertaining to voltage doubler operation. So, let's return to the voltage doubler circuit and discuss circuit operation, including current flow for C1 and C2 on both the charge and discharge cycles. We'll begin with the review of the charge path for C1 on the positive alternation of the input signal, which you recall forward biases CR1. Then, on the negative alternation, C2 is charged by forward biasing CR2. Now, during the conduction time of CR1 and CR2, several actions are taking place. One is, while CR2 conducts, C1 discharges. Its discharge path is down, across, up through the transformer secondary, then down through the conducting diode CR2, up through the load, and back to the positive side of C1. Just as C1 discharges during the conduction time of CR2, C2 will discharge during the conduction time of CR1. Its discharge path is down, up through the load, across, up through the now conducting diode CR1 and the transformer secondary, then back to the positive side of C2. Now we should note at this time that C1 and C2 not only discharge through the paths just shown, but they also discharge through one another. And of course this is true of any series capacitance network. Also true in the circuit is the fact that the diodes are actually operating only a short period of time, where they're acting as electronic switches which allow the energy that has been used by the load to be replaced. The diodes conduct only for a short period of time because once the capacitors have charged, the voltage felt on the capacitors is also felt here on both diodes. And this acts as a bias. Now the only way that the diode can conduct is for the input voltage to exceed the bias on the diode. And this occurs during the peak of the input cycle. The load on the circuit also affects ripple amplitude. The greater the load, the longer the diodes conduct, and the greater the ripple amplitude. Ripple amplitude, therefore, is dependent upon the value of the load. Ripple frequency remains the same, twice that of the input. However, as ripple amplitude increases, filtering becomes more difficult and average voltage decreases. Now that circuit operation on both charge and discharge cycles has been discussed, several important points should be re-emphasized in voltage doubler operation. First, most important in voltage doubler circuits is peak voltage. And peak voltage equals nearly twice the peak voltage of the transformer secondary. The reason is that the output voltage is developed across C1 and C2 in series. Also important in voltage doubler circuit that we discussed is the output ripple frequency, which we learned was twice that of the input frequency. And the reason it's twice the input frequency is because the voltage doubler used full-wave rectifying action, thereby developing an output pulse on both the positive and negative alternations of the input signal. In this lesson, you've learned the construction and operation of a voltage doubler, which is another form of power supply. All types of voltage doubler circuits operate on the same basic principle. Your understanding of this principle and the circuit will not only aid you in maintaining voltage doubler circuits, but will prove a valuable aid in all your future electronic studies.